Pizza Y. Let me check your test results are out or not. After you get your test results. Yeah, Sunday, not Sunday, Saturday. Right, so if you have any questions from the first law of thermodynamics, you can let me know what we did previous class. So it's the equation change in internal energy equals to change in heat plus change in work done. And we saw for systems that weren't gas systems or gas, their syllabus is more focused towards gas. So we have a chapter in the future called gas laws where we'll again revisit this, okay? The ones that I've done here, these are all for non-gas systems. All right. Right, so we did the lamp, we did the water heating system. These are miscellaneous examples. Okay, so I'll do review questions. You'll find that there are some questions, just random things like a rock falling or this one. With reference to first law of thermodynamics, show that the internal energy must be supplied when water is boiling, for instance. Okay, so these kind of questions are what you can anticipate. But most of the questions that we get, they're from gas laws. Because a chapter main focuses on how gases behave. Okay, so we'll be doing that eventually. We are at the last leg of our thermal physics. So today we'll start specific heat capacity, latent heat of fusion and vaporization. With that, the chapter would be over. The thermal physics part. Then we have gas laws. Gas laws is the second topic. We'll start that hopefully next class. So yes, go to page 49. Right, I already mentioned that this particular topic, it's very small. It'll take me 10-15 minutes. It's mostly general knowledge, okay? This is the different types of temperature scales out there and how do we find temperature generally speaking. So if you look at the syllabus is actually bigger than what the content is. But that's actually a lot of information. Our topic is actually smaller than that. So it says that understand that a physical property that varies with temperature may be used for the measurement of temperature and state examples of such properties. Density of liquid, volume of gas, constant pressure, resistance of a metal, EMF of a thermocouple. So these are the ones that you need to investigate and figure out. How do they help us make a thermometer? Okay. Do we have any questions from this that has appeared in our exams? No, not anything so far. Once upon a time, very long back, like 2008, 9, 10, right? There were questions of thermocouples. So thermocouple is there. So I'll just show you some thermocouple examples out there. Okay, that's it. Understand the scale of thermodynamic temperature does not depend on the property of any particular substance. So this is something important. We'll be seeing that. Learn how to convert your temperature. You'll see that A level say it's always 273.15. If you don't use 273.15, you lose marks. Okay, so it's 5 significant figures, 2 decimal places value. Understand the lowest possible temperature is 0 Kelvin and is also known as absolute zero. So yeah, essentially that's what we're gonna look into. So let's first try to understand what makes a thermometer. So if I want to make a thermometer, what is the criteria that my material must fulfill? So it can easily be found from a graph. And what you need to know is, let's say my x-axis is temperature, degree Celsius or whatever the scale is. Okay, so that's your temperature change. And my y-axis is certain property, any property. It could be volume, expansion, any kind of property out there, right? First and foremost, for a thermometer to be possible, your line has to be a straight line. So it has to be a what relationship, linear. So if your material does not show linear relationship, you can't have a thermometer. So if you want to make a thermometer, whatever property you're looking for must have what? A linear relationship. Secondly, it can't have repetitive values. Let me explain what is not possible. So what if you have a graph that goes straight like that, right? And then it eventually falls down like this, okay? So there is a what relationship to begin with here, linear, right? But the problem is, if you look at this graph, or I'll show you another version. If you look at this graph, for instance, right? This can't be used as a thermometer for a couple of reasons. Number one, which is not a what relationship, linear. That's the most important one. Now, secondly, there is another problem. What is that problem? The second problem is that for one particular temperature, right? Or let's say if I bring this here, property value, there are two temperatures possible. So let me explain what that means. So let's say my volume is X. This is the y-axis is my volume. Okay. So let's say y-axis is volume, and you can notice that when your y-axis is volume, here, V, right? For this one volume, how many different temperatures do you get? Two. That's not a thermometer worthy material, okay? So your thermometer material must be of such a type that it can't show two values of temperature for one particular property, okay? So what does it mean? It means that, let's say your expansion is your quantity, your volume expands to 10 centimeter. Now it will be 10 centimeter at two different temperatures. Would that be a good thermometer? You get what I'm trying to say? So the length of my liquid in the thermometer will be 10 centimeters at 15 degrees Celsius, and also it rises and then falls back to 75 degrees Celsius, also 10 centimeter. Would that be an appropriate material to use? No. Why? Because what's the problem? The problem is that at any given temperature, I'm now confused. Is it 75 or is it something else? Like, look at this one. At that particular volume reading, right? This volume reading, what are the temperatures I get? I get a low temperature, I get a high temperature. So therefore, this material, right, this property graph can't be used as a thermometer. So the only material that can be used as a thermometer is something that has a linear relationship. And secondly, it must have no two repetitive values, okay? Can I use a material that has a decreasing graph for my thermometer? Let's say the graph goes down like that. Can I use that for a thermometer? What do you guys think? So let's say there's a property that goes down as temperature goes up. Will I be able to use that particular material as a thermometer? Yes. And there is something like that. What is it? Where temperature increases, a property decreases, and we use it as a thermometer. Thermistor. Thermistor, as temperature increases, what happens to the resistance of your thermistor? Decreases, right? And we can use that as a thermometer. Thermistor has some issues. It's usually a curve, right? But there are ways you can make it into a straight line. So the point is that you need to have a linear relationship, and you need to just make sure that no two repetitive values are out there. You get my point? So if I want to make a thermometer, that's the requirement. So what are things that have these properties? So after investigating, we found that there are liquids that do that, and the liquids expand when you provide heat to them. So we can make a thermometer out of it. So how does a liquid in glass thermometer work? So you have your glass chamber here, and in the glass chamber, you place your liquid. And what happens is, as the temperature rises, right, the liquid will what? Expand. And when the temperature falls down, what does the liquid do? Contract. And the amount by which the liquid expands and the amount by which the liquid contracts is linear, which means that I can actually break down this axis into equal divisions, and I can then use that information to find the temperature. But what if your liquid for first 10 degrees Celsius went this much, for the next 10 degrees Celsius, it went that much? That is not a linear scale, and that is not a good material for a thermometer. But you can use sensors and programming to make a thermometer out of that, okay? So it is possible using computational processing to make that happen. But if you're talking about like a more very basic thermometer, you take your glass thermometer, in your liquid in glass thermometer, what is the so this is your liquid in glass thermometer. So what do we use in this? So this one uses alcohol inside it. Why do we use alcohol here? Because alcohol has a what property with temperature? Linear. So for every degree Celsius increase in temperature, alcohol expands exactly the same amount. So 1 degree to 1 centimeter, 2 degree to 2 centimeter. Now, whether it will be 1 centimeter or 2 centimeter actually depends on like what structure thermometer you have. If you have a very narrow bore, right, then the liquid will expand more, right? And if you have like a very wide bore, the liquid expand less. So that's something you don't have anymore. It was not there in your O levels as well. It was called sensitivity and responsiveness, if you remember. We need to know the words, right? But we don't need to know the function, design, and features of a clinical thermometer. Like, this is called the bulb of a thermometer. This is called a bore. Then there's like a scale here. There's a glass on top of it. Constriction it is a night, but mercury thermometers, they have a constriction, right? So those were there in a very old syllabus. Now we don't have it anywhere. Ekene we have it. Ekene we have a bit of it. We have something called sensitivity and responsiveness. Okay, we'll get to that in a minute. So yeah, this is your liquid in glass thermometer. So what do you do in a liquid in glass thermometer? You place a liquid inside that has what relationship with temperature? Linear relationship, and then you just provide heat and it expands, right? So linear expansion. What kind of liquids show linear expansion? So you have alcohol, and what else? Mercury. What doesn't show linear expansion is water. So you don't have a thermometer that's made with water inside it. Okay, water has strange behavior. I think I talked about it. If you heat water, it expands, and then if you cool water, it contracts. Fine, right? But as you keep cooling, at one point it again expands. That's when it becomes ice, right? So that's why water can use for INR. So yeah, that's liquid in glass thermometer. Are you okay with what a liquid in glass thermometer is? Do you have any questions? So liquid in glass thermometer is a thermometer in which we use liquid. And what property of the liquid do we use for our thermometer? The expansion of the liquid. Okay, so that's liquid in glass thermometer. The next one is thermocouple. I will come to that in a bit. There's a math from there. The other one is volume of a gas-based thermometer. So what's this volume of a gas thermometer? This used to be there in O levels. They got rid of it. So this is a thermometer you can make, actually. See how I make the thermometer. So you take one of these things. It's called a volumetric flask. Okay. And then what you do is you place a small amount of liquid here, preferably a liquid called, not liquid actually, a pellet of sulfuric acid. So like a blob of sulfuric acid, and the sulfuric acid can actually move around. So you have your sulfuric acid that can slide up and down. Think of a water droplet stuck in a straw. Do you understand what I mean? There's a straw and there's a water droplet inside. Sometimes you'll find it's just stuck there, right? So this is that sulfuric acid pellet. And inside this chamber that you have here, you have gas, right? Now it turns out there's actually a relationship between pressure, volume, and temperature. At constant pressure, volume and temperature are what? Directly proportional, right? This one is called we don't have the name anymore in our syllabus. It's called the Charles law. So the Charles law states that volume and temperature are directly proportional, given that what is constant? Pressure. If pressure constant we keep the what of the container open? The top. So as you keep the top of the container open, what only acts on the top? Atmospheric pressure. So because atmospheric pressure is acting here, there's a constant pressure acting on the system, and there's gas inside it. And when you heat this gas, you'll start to notice this pellet moves upwards. And the amount it moves upwards is actually linear. So what we do is we place a scale on the side, it's like the scale rakhe, and that scale has divisions in it, equal divisions. And using that, you can actually find your temperature. This is a volumetric way of finding temperature. Is it okay? So once more, you have this chamber here. There's a gas inside, trapped gas. And as you heat the gas, what does the gas do? Expands, right? As it expands, it pushes the pellet outwards and the pellet moves out. Turns out the amount of expansion is directly proportional to temperature. So the more temperature you provide, the more expansion takes place. And then, you can use that as a thermometer. This is very unreliable, okay, this thermometer, because the amount of energy that the flask is taking in, right, is not going to be instant. You have to first heat the flask, then the flask will heat the air, and then the air will expand, right? So there's a lot of energy transfer taking place, so the process is not very effective. But yeah, this used to be one of the first ever thermometers out there, okay? So that's the volume-based one. Then we have digital thermometer. This is very straightforward. It's basically using resistance of a thermistor. So it O-level so low. It's a sensing circuit, if you remember. So you take a battery and you place your thermistor here. And what do you place next to the thermistor? Does anyone remember? Yeah, fixed resistor, correct. A fixed resistor, and you place your voltmeter across what here, so that the temperature and the voltage is directly proportional. Do I place my voltmeter across the thermistor, or do I place my voltmeter across the resistor so that the temperature and the voltage are directly proportional? Essentially, I'm asking you, what will happen that will make the increase in temperature cause the voltage reading to increase? Where do I need to place my voltmeter? Yeah, let's try. Hopefully they'll not ask about this in the exam, but let's see though. As temperature increases, what happens to the resistance of a thermistor? Yeah, so let's write that down. The chain of events, I hope you remember. As temperature increases, the resistance decreases. As the resistance decreases here, what happens to the voltage here? Decreases. Wouldn't that be opposite to what I want? What did I want initially? I wanted an increase in temperature and a decrease in voltage, right? That's not happening here. So how do I achieve that? What do I do? Yes, exactly. You guys remember. So you have to place it on this side. So if you place your voltmeter on this side, you'll find that yes, the voltage decreases on that side, but as you know, voltage is shared, right? So if the voltage decreases on this side, what happens to the voltage on the other side? It increases, right? So finally, I have an increase in temperature that matches with my increase in voltage. I can use this setup as a thermometer. It's a digital thermometer. Now, there's a small problem with this thermometer. The changes are not linear. So to make them linear, we usually use a calibration system. And that calibration system you had in your AS, you remember that they had these graphs and measurements chapter where the divisions were changing, and they used to ask you why the division changes. Do you remember what I'm talking about? AS ছিল, it's not been a year. ভুলে যাওয়ার কথা না তোমাদের। এই যে these stuff. Calibration, you definitely remember. এই যে এরকম question দিত না যে why are the gaps not equal? So what change causes the gaps to be like this? You remember these questions, right? So a thermistor-based thermometer will not actually give you a straight line. So the scales will be a little off, but it'll give you temperature, right? It's just the temperature spacing wouldn't be equal, because the temperature change doesn't cause equal change in resistance, okay? So the linear part is not there, but yes, there's some advantages of that thermometer. We'll see in a minute. So yeah, this is the digital thermometer. And the other one, modern day version, your syllabus doesn't allow you to use it, but it's there. What is it called? Thermal cameras and infrared thermometers. What do? You just point your thermometer at a location. What does the location radiate? Infrared. And the thermometer picks up that infrared and it gives you an estimation of the temperature, right? It's generally considered to be not accurate, okay? Because the heat that's coming from your material doesn't directly come into your sensor right away. Also, there's energy loss in the way. So, it's not the best thermometer out there. It gives you a good gauge, if it's hot or cold, but not precision. Okay. So yeah, these are the thermometers out there. Now, what are the scales of thermometers based on? So thermometer scales that you have, centigrade scale, it's called a Celsius scale as well. You have Fahrenheit and you have Kelvin, right? So these scales are actually made based on reference material. So let me give you a small idea about how thermometer scales are made. You don't have that in your syllabus, but let me explain. So let's say I want to make a thermometer of my own scale, not a thermometer. Like I want my own scale, not degrees Celsius. I don't like Fahrenheit. I don't like Kelvin, right? I want my own scale. What do? I'll first have to take a reference material. It could be anything. It could be a liquid. It could be a solid, preferably a liquid. And then what I do is I freeze that liquid. The moment the liquid freezes, right, it's called the freezing point. I consider that point to be 0. And then I heat that liquid. And the liquid heats up and heats up and heats up and heats up, and then it boils. That's called the boiling point, obviously, right? So that's the upper point and lower point. I consider the boiling point to be what? Always 100. And I always consider the freezing point to be what? 0. And then what I do is I split every number in between equally. So I have like a scale. And that is how you make a scale. Now, that's how we made a scale for degree Celsius. So if you see degree Celsius temperatures, right, they seem like, very oddly accurate. 0 degrees what? Ice. 100 degrees what? Boiling water, right? That's because the degree Celsius scale is made with what as reference? Water. That's why it matches perfectly. So you'll find like alcohol-based thermometers, right? A Fahrenheit scale. it doesn't really make good sense. If you're using a Fahrenheit scale, right, you'll find the temperatures are very odd. I mean, they use it in many countries where it snows a lot, right? But if you use Fahrenheit scale and you use the temperatures for freezing alcohol and boiling alcohol, do you know what the temperatures are? So 0 Fahrenheit is when alcohol freezes, and 100 Fahrenheit is when alcohol boils. Do you know at what degree Celsius alcohol boils? 78 degrees Celsius, right? And the Fahrenheit scale is 78 degrees Celsius is like the 100. So that's how the conversion takes place. So point is, if you want to make the scale of your thermometer, you need to choose a liquid and you have to find its boiling point. The boiling point would become 100 and the freezing point would become what? 0. And that's how you have your thermometer. And back in the 1800s, right, everyone had their own scale. Somebody used water, somebody used alcohol, somebody used paraffin, and everyone had their own version of it. So what happened was, it's not a linear liquid. So what happened was it was getting out of control, right? So eventually they realized that you can always have a new scale, but that wouldn't solve the problem. And finally they realized they have to look for something else as a reference. And they chose arguably the best thing to choose, the kinetic energy of particles. And that is called the absolute scale, okay? Because there's no point of confusion there, because kinetic energy is universal. You go to a random planet out there, you might not have water or alcohol there, but the particles will still have what there? Kinetic energy, right? So that's considered the absolute scale of the universe. So the lowest temperature you can achieve using the kinetic energy scale is when particles have what kinetic energy? 0, right? And that is called absolute 0 or 0 Kelvin. And from there onwards, we keep increasing the temperature, and that's the Kelvin scale. So the Kelvin scale is based on what in your matter? Kinetic energy. Okay, not energy, kinetic energy. Because once you go to 0 kinetic energy and then you further take energy away from a material, there's no energy to take away. So you can't go any further lower, right? So the K is 0 right now. And since measurement of K is your temperature, right? There's nothing else that you can take out. So it's just the end of it, right? So yeah, 0 Kelvin is the lowest attainable temperature out there. You can obviously keep going higher. There's no end to it, okay? So yeah, these are the scales out there. For our syllabus, strictly, right? It's only Kelvin scale. We won't be using degrees Celsius, Fahrenheit, absolutely not. It's only going to be Kelvin scale. If you're provided degrees Celsius, you have to convert them into what? Kelvin. Do you know the conversion? Yeah, you have to add 273.15. It's given in the syllabus. It's here as well. So always convert degrees Celsius to Kelvin for all math. I'll say, even if you think that you don't know what to do the math, at least do the number conversion, degrees Celsius to Kelvin. There's always 1 mark for it, okay? And yeah, that is it. So just remember that in your A levels, the conversion is a little different. Different one are to detail lage. It is this one, 273.15. If you don't add the 1.15, you lose marks, okay? So it's careful way. So yeah, this is your temperature scale process. I'll just show you one more thing before I give you some notes on this, which is the working of a thermocouple. So what's a thermocouple? Does anyone know? Yeah, right. And how does it show you temperature? Okay, that's actually good enough for what we're trying to do. So the way you create a thermocouple is you take two things called a hot junction and a cold junction. Okay, look at the process. I'm going to explain for you. This actually came in the exam, like, way back, but it was there. So let's see. So this is called the cold junction. Cold junction is, the name kind of gives it away, it's the lower temperature. And this is the hot junction, that's the higher temperature. And what we do is we take a wire, let's say there's liquid inside this, okay? We take a wire from here to there and we connect it. It's a metal wire. And as you connect a metal wire like that, what happens is energy transfer takes place from where to where? From the hot to the cold, right? Because the temperature is higher here and lower here, temperature, energy transfer takes place. Now, what we do is we connect another metallic wire across it and we place what on it? A voltmeter. And it is found that the voltmeter starts to show a reading. It's a very sensitive voltmeter, so it's a millivoltmeter, but you'll start to notice there's actually a reading here. Why is there a reading? So it turns out, when this is your hot junction here, right? High temperature, high energy. Who carries the energy from the hot junction to the cold junction? Electrons, obviously. Do you remember what was the definition of, or what had a definition, energy transferred per Coulomb charge? Current. What had a definition, energy transferred per Coulomb charge? Voltage. Voltage is the amount of energy transferred per Coulomb charge, right? So এখানে যেটা হচ্ছে, from this side to that side, you have, from the hot junction, right? You have energy transferred, and the energy was carried by what? The electrons that go to the other side, right? To the cold junction. And the voltmeter picks up the value of energy here. This is the energy at the hot junction, and the energy there, that's the energy of the what? Cold junction. So you get a voltage here, V1, and you get a voltage here, V2. The voltmeter will show you what? The potential difference, right? And turns out the voltmeter's potential difference, right? It's directly proportional to the change in temperature. This is important. The difference in temperature, not the temperature. So when you have a voltmeter here, the more the difference in temperature, the more the voltage will be. Okay, difference in temperature. So how can we use this to find temperature? Like, how do you use this device? So what you need to do is, this is what you do. You take a hot junction and a cold junction first, and this is work before you start measuring temperature. And then what you do is you set their temperatures of your own values. So 100 degrees Celsius and 0 degrees Celsius, like ice, okay? And then you place your voltmeter here and you observe the voltage reading here. This process has a name. It's called calibration, okay? So calibration korba. So you see that the voltage here is 10 millivolts. What temperature difference gives you a temperature of 10 millivolts? Yep, so just note that down. That difference of temperature difference of 100 degrees Celsius gave me a voltage of how much? 10 millivolts. Now what you do is take out this, whatever this is, like, you know, and then place your material that you want to find temperature. Okay, so you don't know what the temperature is, and that's the material that you place here. And then what you do is connect the wire again, okay? And this time you'll again get what on your voltmeter? A reading, right? So that reading is, in this particular example, let's say 24 millivolts. Can somebody tell me what's the temperature of that? 2,400 or 240 or 2,400. Acha. So you have to do something called unitary method. Okay, how? If a change in temperature of how much? Change in temperature of 100 degrees Celsius gave you 10 millivolts. What change in temperature, right? What change in temperature would give you 24 millivolts? So if you do that, what's the change in temperature? 240 degrees Celsius. That's the change. Now, because this is at 0 degrees Celsius, I can directly say how much is that? 240 volts, right? The problem is the question that came in the past paper, this wasn't at 0. So that's not a problem eventually. Why? Because if this is 40 and you find the change is 240, what is the other one? 280, right? So normally if you were given an option to make a thermocouple, right, it would be best if you consider this to be what? 0. Why is that so? So that whatever the change is the temperature. You get my point? But there's a problem with 0 degrees Celsius thermocouples. Can you maintain the 0 degrees Celsius? No, right? It's ice. What will it start to do over time? Melt, right? So jeta kora hoy, we usually take this as a room temperature. And then that's 25 degrees Celsius. You do your math and you find change is 240. So what should the temperature be there? Yeah, 25 plus 240. Okay, so it's a unitary method process. It's called a thermocouple. My question is, why so many thermometers out there? Why couldn't we settle down for one? But if you look at this, we're still looking for thermometers, right? So why is it so like so many variations out there? What's the reason behind this? So the reason eventually boils down to 3 things. Number one, durability. Like, can you use this everywhere? And then will it survive everything? Will it? No, right? This is made up of glass. It is not going to work well if it's been moved around too much. It will crack and break. It is going to have issues if you place it in what liquid? Very high temperature liquid. So an example of this would be, and you try to tell me what would be a better solution. Do you remember extraction of iron? O levels, so you probably had extraction of iron, right? So there are different temperature stages where you extracted iron, and they had different properties, right? So there's something called cast iron, the wrought iron, right? Pig iron. So there's a temperature for wrought iron which is 4,200 degrees Celsius. That's when you have to extract it. So I need to know that the liquid is 4,200 degrees Celsius, right? Which thermometer do I use? So let's go through all of them. Can I use a liquid in glass thermometer? No, there's absolutely no glass out there that will survive at what? 4,200 degrees Celsius. So if you place any thermometer in that, it'll just melt, right? So that doesn't work. Can I use this volume-based thermometer? No, right? Then my glass chamber has to be in that 4,200 degrees Celsius sludge color, or get the melt color, right? So that's what. Can I use a thermistor? No, the thermistor will vaporize. You place your thermistor in the chamber, right? It vaporizes, it turns into gas. You wouldn't find anything left over. So it all got this now. Can I use a thermocouple? How? Well, wouldn't my thermocouple melt? Then what do I use? Now, the camera is the modern invention. Also, the camera gives you surface temperature. I want to know what's inside. Okay, surface temperature. Right. Yeah. So the answer is you use a thermocouple. And what you do is when you use a thermocouple, the metal that you use, right, is a metal that you use for a metal that doesn't melt in iron, titanium. So titanium has a melting point that's much higher than molten iron. So take that titanium junction and place it in the iron. You have your temperature. So that's what you do. So the thermocouple is very versatile. You can use it for any temperature out there. You want to know the temperature of molten lava? You can use it. Just put that titanium rod in the molten lava and find the change in temperature, right? So that's one advantage. Artegenage, the other thing, so that durability was the first one. What's the other property that you look for in your thermometer? It's responsiveness. Responsiveness মানে হচ্ছে how quickly does it give you your temperature. So এখানে the most responsive, do you know which one? That gives your temperature right away. Liquid in glass thermometer. No. Liquid in glass thermometer is actually the least responsive, because do you know when you measure your body temperature using a mercury thermometer, is it instant or do you need to wait some time? Yeah, so that's not it. Infrared is actually instant. Yes, very responsive. Yeah, the electronic ones. Okay, so thermocouple is instant. Diva temperature ashbe. Digital thermometer or same ashbe. Digital thermometer tao ekটু time লাগে, but thermocouple is very responsive. Okay. Can you tell me which one is very sensitive? Sensitive means that it can measure very small changes. Thermocouple. So eventually you'll notice thermocouple is actually pretty good. It's one of the best out there. But the problem is that you can buy one of these. What do you need to do? You have to make them all the time. Okay, they can't be found like in the market. So it's very responsive. It's very sensitive, but it has this drawback. The drawback is it's too sensitive. So what does the reading do all the time? Fluctuates. Okay, so you place it somewhere, you'll find that temperature never settles down because it picks up such small changes. It's always changing. So yeah, there are pros and cons for all thermometers. You eventually have to settle down for what suits your needs. Okay, so yeah, that's all we have about thermometers here. I'll add a few more information here, but before that, just quick recap. Graph. What is this graph here? So the green line that you see there, the blue line is what a thermometer should look like, or the red line. Property one, it's like volume, expansion, things like that, the properties that change, right? So these are very good for thermometers because they have what relationship? Linear. That's the first thing you look for. Does your thermometer show linearity? Okay. Then you look for, does it show a value twice or not? So if a thermometer has something that the graph has two values that repeat at the same property, right? You can't use that as a thermometer. So if your material was this, for instance, right, that would be a very bad thermometer. Why? Because let's say the volume is 10, right? How many temperatures do you get at 10 volume? 2. You wouldn't know that. The thermometer that you're looking at, the volume shows 10, right? Is it the lower temperature or the higher temperature? You wouldn't know that, right? So if your material repeats a property twice, it's not a good thermometer material, okay? So we finally settle down for some materials out there like alcohol, mercury, most metals, to be honest. And yeah, that's it, okay? So is thermocouple durable? Yes, thermocouple is very durable. In fact, the most durable. Can we measure the temperature of the sun? Oh, by the light. We have it in our syllabus. It's called the Wien's displacement law. So by looking at the color of light, you can say how hot the object is. But there's a catch. It only works for stars. Yeah, so that's why you can't use it anywhere else. It's just stars, not even planets. There's the Doppler shift that tells you how fast they're moving away. But if you look at a star and you look at the color of the star, it actually tells you what temperature it is. The different temperature give you different colors. It's like flame test. How do we know that? So we have tried to cool down hydrogen gas till the point where the molecules are, the term they use is suspended animation. So it's like stuck. They're not moving anymore. That's when we know what is their K, 0, right? And the temperature that happens to attain that is 273.15. That's one way of achieving it. But there were problems in that experiment. It's not truly absolute zero. So the way they eventually found out is what you do in your O levels. You plot a graph for temperature versus pressure in degrees Celsius, and it's a straight line. And then you extrapolate that line, and you keep going back. This is the linear relationship, and you keep going back and find where it doesn't meet the x-axis. And with that precise extrapolation, it's always 273.15. So that's how we know it's attainable. But yeah, they have actually tried it as well, and it went to 273, not 0.15. There were some issues there. Okay, so that's the experimental problem. Which material shows? Oh, so there are materials like water. Water has a graph that looks like this. So it'll show temperature twice at the same place, right? So density of water. Okay, so therefore you can't use water as a thermometer because it expands when you heat it, right? Then you heat it further, it again contracts. It should continuously expand, right? It doesn't do that. So there are materials that do that kind of behavior. Okay, that's thermometers. Any questions? Talking about the borough. It's just it's there in the syllabus, so I had to go through it. So I had some notes out there. তোমরা এখানে যেটা চাও copy করে দাও, আচ্ছা? I'll add just small briefs about each thermometer out there. The change in wavelength of galaxies as they move away from an observer due to the expansion of the universe. So they start to move away from you, so they appear more reddish in color. Yeah, it's because of something called Doppler effect we had in our IAS. So wavelength increases, so they become red in color. School. I have to do further study later on, but that's it. Masters in school physics. There's actually a course like that. They do it in the UK. It's called BEd, Bachelor of Education. So that's what they have to do if you decide that you want to be a teacher. So the Bangladesh provide foreign, as far as I know. Yeah, you're actually overqualified. Yeah. No, I mean, there's a point where it'll start to become boring for me. I mean, whenever you take something professionally and you find it enjoyable as a hobby, it doesn't become enjoyable anymore. So whenever you have to work for something, it just loses the charm. Yeah, so people who have dreams of becoming astronauts, right, never become astronauts because that first year when they put you through military training, right, you give up. So eventually the people who actually become astronauts, so they're not physicists, they're military people. Yeah, exactly. They're pilots. All of them are pilots. What? I didn't think of it. It's like minimum requirement for your A levels. Option what else do you want to say? I was saying statistics this year of subjects taken in UK, for example, internationally. Number one is English literature. Number two is philosophy. Number three is history. Number four is geography. That's what they're doing. So Bangladesh, you're like forced that subject. It's physics, chemistry, and math. Sometimes there's bio. That's all it is, right? But they have full option. They can take whatever subject. They take music before physics. So I saw physics is like much lower than music. I didn't even know that it was a music A level subject. That's what they end up, doing things. Okay, let's move on for a topic today. Right, page 50. Let's go to page 50. So this is a recap of O levels. There's nothing new to actually learn here. There's a lot of new math to do, and the math is basically like a different approach. So there's nothing new to be learned. I will repeat for you. So first, let's define and use specific heat capacity. I want you guys to recall this. What specific heat capacity from your O levels? Pi. Right. So specific capacity was the amount of energy needed to raise the temperature of 1 kg of a substance by 1 degree Celsius or 1 Kelvin, right? Why is this number helpful? It allows you to understand which material will heat up more easily or will take more effort. And the higher the specific heat capacity value, the less easy or less likely the material is to heat up. So something like water has a specific capacity of 4,200 and aluminum has a specific capacity of 700. Which means that when I provide 4,200 degrees Celsius to water, temperature rises by how much? 1. Whereas I provide only 700 to aluminum, how much does temperature rise? Same, 1, right? So you see it takes less effort for aluminum. So specific capacity gives you a measure of how much energy your material needs to raise its temperature. And higher the value, most likely it's not a good conductor or it's an insulator, right? So the energy transfer doesn't take place that well. And that's more or less it. And metals and solids have what specific capacity, high or low? Metals have what specific capacity? Low, right? And water has very high because water has strange behavior. What about gases? What kind of specific capacity do gases have? Extremely high or extremely low? Extremely high. Why? Because gases, the particles are so far apart. When you heat gas, right, it takes a lot of effort for the energy to be transferred. Whereas solids, the particles are already in contact with each other. So the moment you provide heat, energy transfer happens instantly. So to raise the temperature of a room, right, using, let's say, a Bunsen burner, it'll take years, literally. Like if I want to heat my room with a Bunsen burner, right, it'll take me years. But if I want to heat a metal with a Bunsen burner, just place the metal on the burner, you'll start to notice the whole burner, like, metal starts to warm up, right? So it takes less effort to heat up. So that's called specific heat capacity. And high specific capacity means the material requires large amounts of energy to raise temperature. Metals usually have low specific capacity. Liquids have high specific capacity. So this is the definition. You still get the definition here, right? So what's the formula for specific heat capacity? So the formula is, and we have to write it properly this time around. O levels in del Q. Why do we use del Q? Not del E or not E, it's del Q all the time. Can Q use for a high? Yeah, because del Q to internal energy na. Del Q equals to what was the formula? MC del T. This is C. And do you guys know there's del T and del theta? When to use del T and when to use del theta? Del theta for degree Celsius নাই যে তোমার হচ্ছে চেঞ্জ যেটা কেলভিনে যদি থাকে রাইট তাহলে থেটা হয় আর T যদি থাকে তাহলে ডিগ্রি সেলসিয়াসে হয়। Okay, it's not important, but just keep that in mind. Like, sometimes you see they provide theta, sometimes they provide what, degree Celsius, right? So del T is for change in which scale? Change in degree Celsius, and del theta is change in Kelvin. Because it doesn't make a difference in your math eventually, but you might be wondering why del T and del theta sometimes, right? So that's where it comes from. Anyways, so why del Q? I was expecting Jeta Parvatopra. Yes, exactly. This is heat. We just did it last class. Del Q is heat provided. Heat provided. Or you can say gain in what energy? Yeah, gain in internal voltage, because it's eventually becoming internal, right? Yeah. Sorry? Del T change in Kelvin. There are T Kelvin theta. Sorry, ulta is degree Celsius. I'm curious. Del T is right? Yes. K is going to be capital, and this is going to be degree Celsius. That one. Just make that change, okay? Again, this is not very important, but just letting you know. M is going to be your what? Mass of what you're heating. C is what? Specific heat capacity. And this one, important, is change in temperature. So yeah, del Q equals to MC del T. That's the formula. You remember, right? This was there in your O levels, right? So yeah, the thing now you'll realize is that with that exact formula, how complicated questions can get. Okay, so they don't add anything new here. There's no new concept to be included here. Just this same equation, but the questions are a little challenging. Okay, so we'll see those questions in a minute. But formula del Q equals to MC del T, and I'll obviously put del Q here. Why? Because we can only find the what? Change. We can't find the absolute value. Absolute the way for diagram. Okay, so the change is this. Okay, so this is specific heat capacity. So specific capacity is the amount of energy needed to raise the temperature of 1 kg substance by 1 degree Celsius or Kelvin. There's something called heat capacity as well. Do you know heat capacity? Heat capacity is the amount of energy needed to raise the temperature of 1 kg substance by what degree Celsius or Fahrenheit. It's the capacity it has. Okay, we don't have that. That's capital C. This is small c. This is specific heat capacity, MC del T. And yeah, as I just mentioned, that these two are how they write this. Okay. Right. So one more time, let's just go through all of this. Specific heat capacity is defined as the amount of thermal energy required to raise the temperature. Thermal energy, you can also say internal energy, because the thermal energy becomes internal energy, right? The quantity determines the amount of energy needed to change the temperature of a substance. It is unit joule per kg per Kelvin, and degree Celsius. So how it turns out, these two values are same. Does anyone remember why? Right. Okay, so your specific capacity in degree Celsius and your specific heat capacity in Kelvin will give you the same value, because the change in degree Celsius and the change in Kelvin is the same. Do you understand what I mean by that? Right. Okay. I'll explain. Don't worry about that. Different substances have different specific capacity. Specific capacity is mainly used in liquids and solids. Gases is very difficult to apply. Because when you're applying heat, right, you can't directly apply heat to the gas. It's also the environment that takes the heat, right? Heavier metals or material, more thermal energy is needed. So, they'll have higher value. This is the formula. Del Q equals to MC del theta. Theta is in degree Celsius or Kelvin. So in the exam, if you write del T or del theta, they'll accept both of them. Don't worry about it. I just gave that just so that you know that there's a meaning for delta t and delta t separately. Okay, so yeah, we'll do the math next class. What preparation do you need to take? You just do